9.2 is linear regression and the coefficient of determination. You have a least squares regression equation. That's the y equals a plus bx. They use it as y hat instead of y, but it means the same thing for us. A is your intercept, b is your slope. You can find the equation doing the exact same thing that we did back in 9.1 when we went through to find r. You go through the same thing. Type in your information to L1, L2, go stat, calc, you want the linear regression, a plus bx. Now you do not have to go through and store it in there. We can write down the equation by hand and still get the same answer. So don't feel like you have to store things. Okay, so in Denali National Park, Alaska, the wolf population is dependent on a large, strong caribou population. In this wild setting, caribou are found in very large herds. The well-being of an entire caribou herd is not threatened by wolves. In fact, it is thought that wolves keep caribou herds strong by helping prevent overpopulation. Can the caribou population be used to predict the size of the wolf population? Find the least squares regression equation relating the variables x equals size of the caribou population in hundreds and y is the size of the wolf population in Denali National Park. Use x as the explanatory variable and y as the response. So they want us to find the least squares equation line. So again, we're going to go stat, we're going to go edit, clear everything out, type your numbers in, and then we're going to go stat, over to calc, and you want that number 8 like we did before. L1, L2 have to be your x and your y, and then calculate. So our A then is 22.36. And then our B is about 1.60, so we have to round it. Now, WebAssign will tell you how many how many decimal places for this A and your B, so make sure that you are typing all those parts in. Now it says graph the equation on your calculator. So we're going to go to y equals, and we're going to type in 22.36 plus 1.60x. Now we're going to hit that zoom button again and stat, because we want it to show on our graph with the points. So there's my least squares line on my calculator. Your influential data pair is a data pair that if you remove it would substantially change the equation of the least squares line or other calculations associated with linear regression. Usually the x value is near the high or low of your data set. So if you usually get rid of something in the middle, it doesn't change it so much. Whereas if you get rid of a really high value, really low value, then it does. Interpolation is predicting values for x that are between the observed x values in the data set. And extrapolations is predicting your values when the x values are beyond the x values in the data set. So extrapolation may give you unrealistic forecasts, whereas interpolation, you're predicting those y values that are inside of the data set. Your least squares line only works for the sample data in the set. So if you have different data, you might get a different equation every time. And it only works when x is the explanatory variable, y is the response variable. So for example 6, we're following what we did in example 5. So in the least squares model developed in example 5, which is the explanatory variable and which is the response variable. So x is your explanatory variable, and that was the size of the caribou. And then y is your response, and that was the size of the wolf population. Can you use the equation to predict the size of the wolf population for a specified size of caribou population? So yes, we can use our wolf population and our caribou population to predict each other. So as you go through this, again, it tells us in the problem that x represents the size of the caribou and that y represents the size of the wolf population. So x is our explanatory, y is our response variable. So we can use the caribou population to predict that wolf population. So our x values are ranging from 17 to 34. So they want to know if we're predicting when it's 21, will you be interpolating or extrapolating? 21's between those two. So we are interpolating. Now remember, this is 1700, 3400. So when you see the number 34, it's 3400, not just 34. So if we want to predict the size then, we're using the equation from the first page. And instead of x, we're going to put 21 in. You're not putting 2100, you're putting 21 because x was in hundreds. Now we're talking about the size of the wolf population, so we're going to round that to 56. You're going to do the same thing for number 6 here. So I want you to go through. You have the Quick Sell car dealership has been using 1-minute spot ads on a local TV station. The ads always occur during the evening hours and advertise the different models and price ranges of cars on the lot that week. During a 10-week period, a Quick Sell dealer kept a weekly record of the number X of TV ads versus the number Y of cars sold. The results are given in the table. So there's your table. The manager decided that Quick Sell can afford only 12 ads per week. At that level of advertisement, how many cars can Quick Sell expect to sell each week? We'll answer this question in several steps. So I want you to go through, find all your parts, and we'll come back together. So the first thing you should have gone through is stat edit and clear everything out. Oh, I gotta go back. So I've got 15, 31, 10. Okay, so then we go stat, calc, number 8. So you should have then Hold on, my numbers aren't right. Let me double check. I did it again, L1. Okay. There we go. That looks better. So you should have y hat. So when x is 12, you're putting 12 in. We get 18.66, so 19 cars. They want to know how reliable is it looking at your R value. So my R value is 0.919, so that's going to be fairly reliable since it's a strong correlation. Number closer to 1, the stronger it is. The last thing we're going to look at is the coefficient of termination, or your R squared. So with your R squared, it is using the variation between your value and the values from your line. So the coefficient of termination is the fractional amount of total variation in y that can be explained by using your linear model. So for example, if R squared is 0.81, we're saying 81% of the variation behavior of the y variable can be explained by the corresponding variation behavior of the x value if we use the equation. The remaining 19% of the variable is due to random chance or the possibility of lurking variables that influence it. So 81% of it actually happens based on the corresponding x value, whereas then the rest of the 100% is that behavior that might be due to random chance or the possibility of lurking variables. So if we go back to look at what you just did, we just found our R value. It was 0.919. R squared, so look at your list with your a plus bx. We have 0.845. So what percentage of variation in the number of car sales can be explained by the adds in the line? That would be 84.5% of it. Whereas not explained adds is going to be the 100% minus your 84.5%. So that means about 15.5% can't be explained. So again, when you're looking at what can be explained using your equation, we're looking at our R squared and you're turning it into a percent. If you want what can't be explained, then you do 100% minus that to get the leftover.